okay, that's step one. And I separate this is what I do personally. I separate my thoughts by a comma. That's a comma right there. This here is a comma. I separate my thoughts by a comma. And every step is a separate thought for myself. So this is how I explain it. Now, that's step number one. Now, after step number one, I'm going to show you the transition state that exists between step number one and the final product. A transition state is a very, very extremely short-lived intermediate in a mechanism. Let me say it one more time. A transition state is a very, very short-lived intermediate, a very, very high energy, a high potential energy intermediate that lives for a very small fraction of a moment during a mechanism. It is the highest point of potential energy during the mechanism. And of course, you know, a high potential energy in chemistry relates to instability. So the transition state is the place where is most instability. So this will be the highest point on the potential energy diagram that we're going to see. So the transition state looks like this. So of course, you know, we have our B there. That's our carbon B. We have our A there. Now connected to A and B at a fraction of a second is the iodide, and it's going to have a partial negative charge, and we're going to talk about why. And the oxygen, which is going to have this oxygen. Oh, I have to draw it black because it's black in the previous drawing. The oxygen is going to have a partial negative charge. Okay, let's see. Okay, so the hydrogen is there. Okay, now that's A. Okay, everything's in order. Okay, so in this, I guess this A carbon is going to have some partial charge associated with it. But at this point here, what we have to understand about this transition state, and usually what you'll see is your professor explain a transition state with this symbol here. You'll see that symbol, and that's the transition state symbol right there, which means it's high energy, you know, all these things, very unstable. It exists for a fraction of a second. It's real, like, imaginary. Don't get me wrong. This subject is already abstract enough, but the transition state is even more abstract because it seems so, I don't know, just fantasy-like. Okay, so this is the transition state here. This is the point where this is the perfect simultaneous point where the leaving group is about to leave, the purple, and the nucleophilic atom is about to attach itself to form the final product. So after this point, we have finally the final product, which is this. That's our B. That's our A. And then attached to A, of course, is going to be the nucleophile that attached itself. It performed the nucleophilic attack. And we have the oxygen. That's the hydrogen. That's a lone pair. That's a lone pair. That's a lone pair. And what do we have? We have the iodide plus this purple iodide. That has its 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 1, 2, 3, 4. 4 lone pairs and a -1 charge. Now, let's talk about some interesting things related to the mechanism before we talk about the rate. Notice in every point of the mechanism, from all the way from day one in chemistry in high school or general chemistry 1 or whatever you took, they always talked about this one rule. They talk about the law of conservation of mass and energy. This rule, and you can even say charge with that rule because that's, you know, kind of like energy or mass or whatever. It's grouped in there. The physicists group it in there, I think. Now, if think about this in step one, the entire charge. Let's not focus on the mass because the mass remain the same. Okay, let's look at the charge. That's the interesting part. Notice how in the step one, the charge of the whole, and this is how you can kind of tell if you got the correct. This is how you can tell if you got the correct mechanism, if you follow this kind of really. In the step one, the net charge of all the atoms and all the molecules put together of the whole thing is -1 in that step. Because the oxygen has a formal charge of -1, the hydrogen has 0, Those two carbons are 0. That iodide has a formal charge of 0. We don't worry about the transition state because it's like imaginary or whatever. It's, you know, whatever. It's weird. Now, the final product step has a charge of -1 because this whole molecule, ethanol, has a formal charge of 0. That iodide has a formal charge of -1, which gives the whole thing -1. So that's interesting about the charge related to the law of conservation of mass and energy. Now, okay, so we've talked about all these things, glorious things related to the Sn2 reaction. It's very beautiful. To me, it is. Now, okay, so now what we're going to talk about is the rate to end everything off. So, and then after we talk about the rate, we'll pick up in the next video about what was that? Oh, we're going to talk about the potential energy diagram in the next video. Now, let's talk about the rate. What is the rate of the Sn2 mechanism? We said that it was second order. So we would expect that the rate would be some A molecule times some B molecule gives us, you know, well, I mean, that's supposed to be a 1. I apologize. Of course, you know, if this was, okay, now, let's just say that this is X. You know what? Let's not worry about those numbers. Let's say that this is X right here, and let's say that this is Y. That's A to the X power and B to the Y power. Well, in this reaction, we assume that X plus Y is equal to 2. And that's true. Let's talk about why it's true. The rate of the Sn2 reaction, of this Sn2 reaction, is the H times the O, you know, this thing. And we're going to talk about this. We're going to talk about this. Don't get afraid. Please don't get afraid of the Sn2 reaction. That right there, -1. Times this thing right here. This. Sorry. I'm not trying my best not to be messy. Oh yeah, wait. The purple. The purple here. The I. Okay. Oh right, I forgot. I gotta put the K up in there. The constant. Oh man, the chemists are gonna smack me if I don't leave. If I leave the constant out, they get very angry. Chemists do. Now I'll put that K right there because that's the equilibrium constant. But that's a whole nother topic. But anyway, we're focusing on the rate now. There's 1. Notice in the middle. Okay, first let's talk about why these two molecules are in the rate. Now notice, in any chemical reaction, the rate is dependent upon, the rate determining step is the slowest step. Or when I say the rate determining step is the step that, or the step in the mechanism that has the molecules that determine the rate law. Now, if you look at step 1 is going to be the slowest step. And the reason that step 1 is, step 1 is the slowest step. Step 1 is the slowest step is because after, step 1 is, I apologize. Step 1 is the slowest step because step 1, I apologize. Step 1 is the rate determining step because step 1 is the slowest step. Step 1 is the slowest step in this reaction. And the reason step 1 is the slowest step in this reaction is because after this slow step happens, everything else after step 1 happens very fast. And the slowest step is the rate determining step. So step 1 is the slowest step. So now notice, there's 2 molecules involved in the slowest step. The nucleophile, molecule number 1, and the electrophile, molecule number 2. That's why the nucleophile is in here and the electrophile is in here. Because those are the 2 molecules that the whole rate is dependent upon. And of course, this is to the first power because there's only one of these molecules. This is to the first power because there's only one of these. I'll say that one more time. The nucleophile is to the first power because there's only one molecule of a hydroxide. The iodoethane is to the first power because there's only one of these involved in the mechanism. And of course, 1 plus 1 is equal to 2. So that's why that's why we say Sn2. The 2 means bimolecular, and this is where the 2 means. Okay, so we finally finished this Sn2 reaction. Hopefully this helps you have a better understanding of Sn2 reactions, and next we'll go to the potential energy diagram of an Sn2 reaction. Have a good day until the next video.